This time though, I'm going to go for autocorrelation of AR1. Going to start simple. The book actually jumps right into an ARP process, which is, in my opinion, complicated for this level, of course. So we'll start with AR1, and then we can go from there. Okay. What does an AR1 process look like?
T equals
mu, okay. We're going to assume it's all centered in mu 0. Keep things easier. I hate putting that to each and every time. So,
x minus 1.
Psi 1, xt minus 1. Did we have psi naught? No. Psi naught would be the mean part. Okay, that is a simple AR1 model. What do we know about AT? ACT. AT is
Independent and identically distributed.
It's IID. From some distribution. What do we want its mean to be? We want the mean to be what's value? 0. And what about variance? We had a notation for it. Sigma squared A. We know from last time, covariance of xt, xt plus h is simply the autocovariance function as like h. H could be positive, h could be negative. The function is symmetric, so whatever happens to the left hand side, it's going to happen on the right hand side. So if you Google, you might find references where people would write this as t minus h. Doesn't matter whether it's h, k, minus h, minus k, same thing. I don't like negative, so I'm going to stick with positive h. Xt psi 1, xt minus 1 plus 80. If you have to write xt plus h, how would you write it? Xt plus h, psi 1, xt minus 1 plus h. T is simply replaced by t plus h. And a sub t plus h.
If I go to the bottom half, I don't go to the top half. Go to the bottom half, square root of the variance they described.
No, the other one. If you have two random variables, x plus y and u plus v, you can split it up and you can write it as covariance of psi 1 xt minus 1, psi 1 xt minus 1 plus h, covariance of psi 1 xt minus 1, comma at plus h, plus covariance of at, comma xt minus 1 plus h, the last bit, covariance of at, comma at plus h. Psi 1 is a constant, psi 1 is also a constant, yes.
Should there be a psi one in front of the xt1?
Yes, there should be. Something's going to happen and it wouldn't matter at all, but you are correct. Okay, psi 1 is a constant there, psi 1 is a constant there as well. So what would happen?
0.
0. If it is just covariance of psi 1, comma psi 1, sure, it is 0. But I've got x's there too. 3162. If you have a random variable x, not a random variable y, you want to find the covariance of ax, comma by. It's a first sequence, right? You tell me.
Just pull the constants out.
Very good. You pull the constants out. Psi 1, if they come out, it will be psi 1 squared. Covariance, xt minus 1, xt minus 1 plus h. There, going to do the same thing. Psi 1 is going to come out. Covariance, xt minus 1, at plus h. Next term, psi 1, covariance of at, comma, xt minus 1 plus h. And lastly, covariance of at, comma, at plus h. What is the value of that? Think logically. Forget about the math part. Think logically. What am I trying to find? I'm trying to find the covariance of a random variable and some noise component. The random variable's got a pattern, the noise doesn't. It's just a random noise component. I want to know the covariance in the sense, how does this observed series relates to some random component?
It should.
It shouldn't, so what should the value be?
0.
0. So that goes bye-bye. It doesn't matter what time index you have. Independent, identically distributed, no matter what t you have, that is going to become 0. Follow the same logic that happens to that one. Same thing. Gone. To do like this, we're looking at variance of editing. It's important. Okay, so I have gamma of h to be equal to that term psi 1 squared covariance xt minus 1, comma xt minus 1 plus h. Covariance AT, comma, AT plus h. Good. From last time, we know since AT and AT plus H are independent of each other, that covariance will be 0. Agreed. So what I'm going to do, I'm going to start plugging in values for H. And that is the reason why I started simple. There is actually an expression that I will derive later, but I don't have to do it individually. I can simply take an entire series, doesn't matter whether it's for p order, qth order, doesn't matter. You can come up with an expression. I'm starting simple so that you understand the process. Okay, so if h is 0, that expression would reduce to psi 1 squared covariance of xt minus 1, comma xt minus 1, covariance of AT and AT plus H, and H plus 0. In terms of covariance and variance gamma naught, it is a variance of what? What am I finding the variance of when I find gamma naught?
Variance of, like, yeah, 1 point to the south, correct?
True, it's all in what of my question. So I know this part, covariance of AT, comma AT is the variance of noise by sigma squared A. I would like to know what that is. What am I finding the variance of?
It's the variance of the series.
Very good, that is the variance of the series. Can I call it sigma squared sub x? I think you put my call it sigma squared sub z. Because what you just said, T, I hate it. Maybe I'm just nitpicking. Can I erase this part? So from the left-hand side, I can rewrite it as sigma squared sub x. It is the variance of the series. Mind you, noise has its own variance. The series that you observe has variance. Good. So one is something that we assume, the other is what you get from the data itself. Right hand side, psi 1 squared, what is covariance of xt minus 1, comma xt minus 1? You've got to read. Things are going to pile up really fast. Covariance of x comma y is just covariance. That's what we call it. But if I rewrite it as covariance x comma x, that is simply the variance of x. Good. So this term will be the variance of xt minus 1. From A here is your standpoint, since x x's are random variables, do you believe the variance of xd would it be any different from the variance of xd minus 1? No. So you've got a bunch of observations that you measure in the series. It's got random noise added to it, and the series has its own variation. So if xd is with a variance of 0.1, or x2 is variance 0.1, x8 will also have the same variance, theoretically speaking. Yes? So I can write this part as sigma squared x. Good. It's the variance of the series. That is a constant, it doesn't depend on time. Agreed? What condition is that? The variance not depending on time. Stationary conditions. You would say, why, right? It makes things easier. Plus, what about the last term? Covariance of 80 on 80. Sigma squared 8. Good. I can read that term to this side. That's what I will have. Sigma squared x times 1 minus psi 1 squared would be equal to sigma squared a. Would it be wrong if at this point I would place that by gamma sub 0? So that's pretty much what I did from there to there, right? Whether it is sigma squared x or gamma sub 0, they are one and the same. Good. Okay. So I'm going to put that as gamma sub 0. Now you might wonder why. Everything is going to depend on the autocovariance function, autocorrelation function. So it is best we represent it in terms of gammas. I wrote this over here, went over there, just so you know that gamma naught is the covariance of the series. Good so far? Okay. If I rewrite this expression, gamma naught is sigma squared a divided by 1 minus psi 1 squared. Good. Right. We did that for h equals 0. There is one other lag that matters to us, because this is an AR1 model. So how far should we go? Up to what lag? Theoretically speaking. 1. 1. So since this is an AR1 model, we can go up to h equals 1. So let's see what happens at h equals 1. We're going to plug in 1 here, and tell me what you get. Left hand side. If h is equal to 1, what will our right to the left hand side ask? Gamma 1. What about this side?
So psi 1 squared multiplied by the covariance of x sub t minus 1 and x sub t. I'm not so sure what we can. So that, yeah, I think the covariance of a sub t and a sub t plus 1 would just be 0.
Okay. The next term would be covariance of AT and AT plus 1. That is going to be 0. Agree? Okay. So gamma 1 would be psi 1 squared. What should we do there? It is covariance of xt minus 1, comma xt. Look at the definition of autocovariance. Oh no, this one is going to be 0. Agreed? Yes. I want to know what that is. I'll give you a hint. I can write that as a extension. Covariance xt plus minus 1, comma xt. Does it click now? Going back to the very beginning of how things started today. What is gamma sub h? Okay, so in this case, what would that reduce to?
Games 1.
Gamma sub 1. This one, technically speaking, we would have x sub t plus, that is the light part, minus 1. But what do we know about gamma sub minus 1? It is the same as gamma sub 1. And that would end up giving us psi 1 squared equals 1, which would mean psi 1 is 1. But we know something about a process where psi 1 is 1. If psi 1 is 1, what can we say about that process? So if you follow the same logic, you end up getting psi 1 equals 1, but that will not make any sense because a couple of ways. One, I know psi 1 cannot be 1 here. If that is 1, you would have xt equals xt minus 1 plus a sub t. That is the first simulation that I did at the beginning of the semester. That's got a name.
Random walk.
That's a random walk, so that's not stationary. So another way to check, if psi 1 is 1 over here, sigma squared divided by 1 minus 1, which is 0, infinity, variance blows up. Yes? Again, if the variance is blowing up, then that tells me it's not stationary. Good?
Will that always be true when h equals 1?
No. So, we have one expression written over there. Can I erase? Going to go back to covariance of xt and xt plus 1. How would things change if I had it as, say, xt comma xt minus 1? Hypothetically speaking, covariance of xt comma xt minus 1. In this case, I'm not going to replace both terms. I'm just going to replace the first one right here. Keep the second one as is. Good. If I kept the second one as is, change the first one, I'll end up getting covariance psi 1 xt minus 1 plus a sub t, comma xt minus 1. Agree? Good. Now tell me what the left-hand side is, following the same logic. Left-hand side. I want a notation for the left-hand side. Left-hand side, Joe. Left-hand side.
Okay, so it comes with gamma 1.
Let's just gamma 1. Right. The covariance of xt, comma xt plus h is gamma sub h. So here it's gamma 1. Okay. I can do the same trick that I did earlier, split the covariances. If I did that, I will have covariance of psi 1 xt minus 1, comma xt minus 1, plus covariance of at, comma xt minus 1. Good. Okay. Don't want to erase that. Can I erase this? We know what a nail one model is by now, or one would hope so. Second term. What would happen to the second term? 0. We are trying to say that an observed series is somehow correlated with noise, it can't be. So that's 0. So I have gamma 1 equals towards going back to, 30 minutes ago. What can I do? Coefficients even.
Pull out the sidewalk.
Pull out the psi 1. I would have psi 1 covariance of xt minus 1, comma xt minus 1 plus 0. What is covariance of xt minus 1, xt minus 1?
Variance, that's good.
It is simply the variance of xt minus 1. In terms of gamma, what would that be?
Number 1.
Near 0.
0.
There's no line.
There is no map. I'm going to teach you a trick. Remember, I mentioned this last class, the lecture before that. Right over here, I wrote J minus I minus J is going to play a huge role in this class. Do we remember? It was right here. I'm not going to let that go either, just like an action. So, x of t minus 1, x of t minus 1. All you have to do call it I, call it J, subtract them. When you subtract, what do you get? 0. So that has to be gamma sub 0. Let's say the logic holds true here. Subtract them. T minus 1 minus t. What do you get? Negative 1. Well, if you say, well, I don't like the order, I want to do t minus 1, you will get gamma sub 1. But we know gamma sub 1 and gamma sub negative 1, they are really the same. So, easy trick. So don't forget, I minus j, g minus I. In simple terms, absolute value is g minus I. Okay. Here I have that expression. So that approach where we took the series and plugged in h equals 1 resulted in that. That cannot be right. And why did that happen? It happens because I put in the series here and I lab that series again one more time to try and find the correlation of covariance at h equals 1. Shouldn't make any sense. Why? You have xt and then you lab the entire series one more time. So we end up getting psi 1 equals 1, that expression wouldn't work. For a stationary series, that is not true. That is the expression that we want. Good? Okay. Great and all, you might wonder, why did we do all this? There is. So, gamma sub 0, we end up getting sigma squared A divided by 1 minus psi 1 squared. One expression. Another expression, gamma sub 1 equals psi 1 gamma sub 0. Agreed. If I divide by gamma sub 0 on both sides, I will get psi 1. Good. Who can tell me what the left-hand side is? The left-hand side is nothing more than the autocorrelation. We don't have to worry about rho sub 0 because rho sub 0 is 1. You are correlating the series with itself. 1 doesn't matter. Is it necessary to go past 1 for an AR1 model? Silly. Theoretically speaking, an AR1 model only goes up to 1 lag. That's it, that's all you need for prediction. So there is no need to go past rho 1. Good. Look at that expression. That expression is telling us, well, if you look at rho 1 is going to give me the value of psi 1 in my model. So I observe a series, I find its autocorrelation, and it simply is telling me, well, you can fit the model easily if you look at the autocorrelation function. Good? So, that's exactly what we're going to do. We've done this before, once, right? I simulated an AR1, obtained an ACF plot, and then I pointed out, oh, look at row 1, it's going to play a role. About to play a role soon. Good? Okay. So, we have an expression for gamma naught, we have an expression for gamma 1, and that's all we need. switch to R,